So this is, I think I have covered this in the bridge course, maybe no. LU decomposition, did I cover it in the bridge course? No. Put something on QR. QR method? No. Yeah. So these methods require a bit of practice. So what I suggest you see how these two methods you learned, but these two methods are very interrelated to each other, and just a minor difference is there to what you are doing right now. So similarly, LU decomposition method is one among them. The idea is you have a matrix A, that is AX equals to B. That means you have a set of simultaneous linear equations. We are still in that field. What we are trying to do is convert this, you can decompose A into a product of two matrices. Okay. And those are two special matrices, that is L and U. Okay. And L here is known as a lower triangular matrix. U is an upper triangular matrix. Okay. So, yeah. So I would tell you that if you suppose, we will dive more into this, but suppose you have decomposed your matrix A into this, A equals to LU. Okay. Then what happens? So you see that LUX equals to B. Fine. I just substituted A equal to LU. LUX equals to B from this. From these two you get this. LUX equals to B. Then what you do? You solve UX. What is UX? Suppose UX, maybe you get say Y. Another vector you will get. Another vector you will get. Agreeing with me? Why you should ask me when I write UX equals to Y, you should ask me why UX is not giving a matrix rather than I am writing Y as a vector. Can you easily see why I am getting a vector? What is the size of U? Say n cross n. What is the size of X? X is a vector. So n rows, one column. Okay. Is this multiplication possible? Yes, it is possible. Because n is same. Then what is the size of the resultant multiplication? The size of the resultant multiplication should be the other remaining parts. That is this and this. So what should be the size? N cross 1. N rows and one column. N rows and one column. What is that? Is it a vector or a matrix? It's both. It's both. But technically it's a vector. So therefore I'm writing Y. So this is like you should think like why, if it is written, why it is written. If UX, I can write it as a matrix, but why I wrote it as a vector? Because I already knew that this will look like a vector. A matrix multiplied by a vector is giving you a vector. A matrix, listen carefully, a matrix multiplied by a vector is giving you another vector. So if you want to generate new vectors and you have at your disposal a matrix, what you do? Multiply that vector with that matrix and you generate new vector. It's a idea of generating new vectors. Okay. Vector is most important to you in every field. In every field, vectors will be important. This same concept you will see, multiplication of a matrix with a vector is resulting in a vector in simple linear regression as a neural network. If I teach you in next semester numerical methods, I will be covering this. Okay. So how linear regression, how simple regression problem can be visualized in terms of artificial neural network. There is something known as multi-layer perceptron, okay, where you can visualize these regression problems. And we will solve a regression problem using MLP, multiple layer perceptron. There you will see more, it gets more efficient if you increase the number of hidden layers and all this. But that is in the next semester. So LUX equals to B, then what you do? First step is you solve UX, and UX is resulting into a vector Y. Okay. Then what is the second step? The second step is since UX equals to Y, now you have to solve only LY equals to B. Just LY equals to B, and it will be pretty easy. Solving LY equals to B will be pretty easy because it's a load. Just through back substitution, you can easily solve this. So you can see like how LU decomposition method is also helping you is another method. It's another method apart from Gauss elimination and Gauss Jordan to solve system of linear equations. But if you see, this is another variant. This is another variant of Gauss elimination. Another variant of Gauss elimination. In Gauss elimination, what you do, you solve the simultaneous equation, that is the matrix A, in such a way that you get which matrix? In Gauss elimination, you have a matrix A, you do all the row elimination. When you reach out to a matrix, what is that matrix? Upper triangular matrix. So here in that method, upper triangular is already there. Upper triangular method is already there. Therefore, mathematicians, they got motivated into framing this method. What if it is giving upper triangular matrix, then what other matrix it can be decomposed? Then they came up with this LU decomposition. Python also has a package for this, a function LU. Okay, just LU. So if you know it calls SciPy, import SciPy, and in that I will show you that just use LU of A. If you just type LU of A, then it will give you what is the lower triangular and what is the upper triangular matrix for A. Now, if I give you a problem that I give you a matrix A and I tell you, give me the L and U, it is going to be a bit hard because you have to solve a lot of equation. I will tell you why. But if you just give to the Python a matrix A and type LU, then it will give you the L and U matrices for which can get multiplied and give you A. This will look into the after lunch class, okay? Because after lunch class I have preserved for Python. Okay, so now you learn the theory, then you see everything in Python in Excel. So why we are learning a new method? We are learning methods after method, but why are we learning? Okay, why are we learning? So every method has its own taste and its use. Every method has its own taste and its use. Okay. Why we learned about LU decomposition is because of this fact. Suppose you have the matrix A, you have this vector x unknown, and you are writing B is the quantity should be equated to. Now suppose consider this quantity Ax equals to B. Sometimes what you do is you suppose B you can think of as the total cost you have in your pocket right now. I told you the morning example, number of tomatoes, kg of rice and all, isn't it? That should be matched with the total cost. You can think vector as the total cost. Okay. Now this cost can change, isn't it? You got your pocket money like this month, today you got pocket money. So what happens? This day, today you have lot of money. And what you do, you spend it. Okay. Then if you spend 90% of it, suppose this is B1, today's spending. Next day you spend. Can you buy the same amount of items? No. You have a fixed amount. So that will be B2. Okay, so sometimes I'm motivating you that sometimes in real situation, you have to solve the same A into X. You have to solve the same A into X as B1, some same A into X as B2. Of course, this will change. Some A into X3 into B3, all these equations. Sometimes you will do like this. In that case, LU decomposition is allowed. Okay. If you have different right-hand sides and the similar kind of left-hand sides, in those situations, LU decomposition is helpful because A into LU, you decompose the matrix A into LU will be the same in all the cases, isn't it? It will be same in all the cases. Remember, in your previous Gauss elimination and Gauss Jordan, you were playing with this also. You are playing with B vector, isn't it? But here I am telling you that in all of these cases, just you need to write A equals to LU, and this decomposition will work for all of these three cases. Bothering about the B vector, which is changing. Hope I'm able to communicate you. Anyway, so I think this we will quite get to know if we do some examples and all. Moreover, like we will see that this LU decomposition is not unique. LU decomposition is not unique. You can have the matrix A, you can decompose into L1, U1, and the same matrix you can also decompose into L2, U2. Okay, so LU decomposition is not unique for a given matrix. We will see some examples, I think. See, I think we have an example over here. I have, maybe I can show it to you. Suppose say A is your matrix over here, 4, 6, 2, 3. I'm asking you, can you decompose into L into U? Can you decompose into a lower triangular into upper triangular matrix? It is a bit hard. It is a bit hard. Okay, but it is not impossible. It is possible. But anyway, I will just show you that this is the case. 1, 0, half 1, then 4, 6, 0, 0. This is 1. Why this is the 1? If you see, this is L, and this is the upper triangular matrix U. Okay. Now I am telling you there is also another sort of decomposition, the same L2 U2, where L2 you can get 2 0, sorry, 2 0, 1 1. Nothing. It's if you get one LU decomposition, you can get another LU decomposition just by multiplying the constants. What is, can you see? I just multiplied the first row by 2. 2. Second row, just I divided by 2. 2, 3. That's how I got another LU decomposition. Can you appreciate the relationship between the two decompositions here? So you can see that the LU decomposition is not unique. I just want to communicate this. Okay, there doesn't exist a single sort of L and U. For maybe this group can take LU different, maybe you can find LU different. It totally depends. Okay. So, yeah, I think this should be enough for LU. This should be enough. I should not write a lot of equations and confuse you. But you got the basic idea, is it? So what is the basic idea? It's another way of solving the system of linear equation. First point. Second point is through the observation of Gauss elimination method, which transforms the coefficient matrix A to an upper triangular matrix. This method got motivated from Gauss elimination that yes, we can decompose the matrix A into L into U, a low triangular into an upper triangular matrix. Okay, we will see that it can be done. It can be done. And I told you that this sort of LU decomposition is not unique. Okay. We saw two examples over here. For the same matrix, 2 by 2 matrix, we saw two L1, decomposition of the same matrix. So therefore, LU decomposition is not unique. Yes, sir. Idea is you can use LU decomposition in finding inverse of matrix. Okay. You can use LU decomposition in finding inverse of the matrices. We will not learn this today. Okay, I'll preserve this for some other class. So, but just to get you an idea, like why we are learning these methods, why we are actually learning these methods. Now, depending on this LU decomposition, there are two very funny looking methods. Okay, same LU decomposition. Okay, and these two methods are very easy to know. Okay, and these are just two variations of the LU decomposition method. Okay, I will tell you in the next slide. LU decomposition you already know about. Okay, LU decomposition you already know that decomposition that you just do A and break it into a product of two matrices L and U. Now, depending on the entries of two matrices, depending on the entries of two matrices, okay, There are two methods. There are two methods. What are these two methods? If all of your diagonal elements in the lower triangular matrix LII, can you see? II means the diagonal elements, isn't it? Ith and jth row are the same. Jth value are the same. If LII, all the elements of the lower triangular matrix is 1, okay, and you have that sort of decomposition, okay, then this method, yes, this method is known as something, okay, something. I'll tell you later, okay. If there is another method, if UII equals to 1, there is another method. But same LU decomposition we're doing. Okay. If LII equals to 1, if LII equals to 1, then there is a method. This is known as always happens. So if LII equals to 1, okay, if LII equals to 1, this is known as, if you solve by LU decomposition, this is known as the Doolittle. Okay, the Doolittle method. Now, if UII equals to 1, this is another method. Okay, this is known as a Kraut. Okay, so I'm just telling you that no need to worry about that. There are so many methods, which one to use, which one not to use, and all. But I'm giving you a survey how people are thinking. Okay, people thought like, see, why they thought of putting LIA equals to 1. They thought that if I put LIA equals to 1, I am reducing the number of unknowns in that matrix. Okay, then the number of unknowns will be decreased, isn't it? Previously, those diagonals were unknown to you. You have to compute those diagonals. Now, if you put those LII equals to 1, you are maintaining n number of unknowns as knowns. So you can understand how efficient it is getting. Are you getting the idea? No. How many of you are not getting? See, we'll see that. Okay, maybe you can appreciate this as LU, and L is a matrix. Can you give me a sub like 3 by 3 matrix? L1100, L21, L220. Give me an upper triangular matrix. Fine. Now I tell you that you have this, you have a matrix A. In matrix A, if it is a 3 by 3 matrix, this is a 3 by 3 matrix, right? So A should also be a 3 by 3 matrix, isn't it? So A should be a 3 by 3 matrix. And A, you already know, isn't it? A matrix you should already know. That's the coefficient matrix. Now, how many elements are there in matrix A? How many elements are there in matrix A? How many known elements are? It is a 3 by 3 matrix. I would have given a Kit Kat chocolate. Then you would have calculated how many Kit Kat bars are there in. But if I tell you that this is a 3 by 3 matrix, calculate the number of elements, that's your confusion. Yes, now we are getting the answer. Yes. So it has 9 elements. 9 elements, 9 known factors you have. Now I am telling you that you are decomposing this into L into U. Okay. And these are all unknowns. Is it this? Do you know? You have to find out. You have to find out, right? Li's and ui's you have to find out. So how many unknowns are there in this matrix multiplication? Can you tell me? 6 on the lower triangular and again 6 on the upper triangular. Fine. 6 plus 6, 12 unknowns. 12 unknowns. 12 unknowns. 12 unknowns on the right. Here you have 12 unknowns. Here you have 9 elements which you know. How many equations you have? Can you solve this first of all? You have 12 unknowns. Okay. Can you solve this? Hmm? Can you solve this? How many equations you will have? How many equations you will have? Sure about that? Let us multiply L into U. L11, U11, fine. Then like this, right? Isn't it? It will be a 3 by 3 matrix again. Yes. So can you multiply the second row with again the first row? So L21, U11. This one will be multiplied with 0, so no effect. Again, this row multiply with the second one. Then am I getting clear to this? Like, is it fine? Is it fine going? Fine, no? Okay. Now next go to the next row. L31, U11, others are 0, so no effect. So this row, second column. L31 times the second column, U12 plus L32 times U22. This one multiplied with 0, so no effect. Now this one multiplied with the third column, right? L31 will be multiplied with U13 plus L32 will be multiplied with U23 plus L33 will be multiplied with U33. Now you have to equate this with the elements of the known elements of matrix A, which is say A11, A12, A13. Isn't it? These are all known to you. These are all known. How many elements are there? 9. How many equations are there? 9. You have 9 equations. Each is an equation, isn't it? Each is an equation. You compare with each element here. So here you have 9 elements. So here you should have 9 equations. Now you have 9 equations, but how many unknowns are there in the equation? So came to know about here 12 unknowns. No, not 6, right? Here you have 6 unknowns. Here you have 6 unknowns. Those are intermingled here. So you have 12 unknowns. 9 equations and 12 unknowns. Can you solve this? Equations and 12 unknowns. Can you solve this? Equations, 2 unknowns. Can you solve? Yeah. Now I am asking you, if you have 2 equations and 5 unknowns, can you solve this? You cannot solve this because you have less number of equations than you have the number of unknowns. Therefore, there is a need for this Doolittle and Kraut method. How intelligently they devise this method, you see. In Doolittle method, they told to 1. Now, if you do LII equals to 1, how many unknowns are you throwing out? If LII equals to 1, how many unknowns are you throwing out? LII only, not LIJ. LII means only the diagonal elements I am making 1. L only, that is Doolittle method. Doolittle method never bothered about you. Doolittle method, since he is little, L. Only lower triangle. Okay. Huh? 3. So if you discard 3 unknowns, how many unknowns you are left with? Now can you solve? Now, on 9 equations you were having previously, and 12 unknowns you were having. That led to impossibility of solving this. Therefore, what you did? You did do little. So you can think of this as L. Okay. LII. Yeah, good. So you can think LII equals to 1. Okay. And in that, you are reducing the number of unknowns from 12 to 9. So now what you have? Now what is the scenario in Doolittle? In Doolittle, now you have 9 equations with 9 unknowns. You can easily solve this. Now let us come back to the Kraut method. In Kraut method, again, he did like, okay, Doolittle already did with LIA. So I should do with something new. So I should do with the upper triangular. Okay, lower triangular is already the same. Okay, these are two different methods. Don't think you should not combine these. Okay. So Kraut method, what he did? He did the upper triangular to be 1. So how many unknowns you have? Again 9. Because 12 minus 3 elements you will have on the upper triangle. So 9 elements. So 9 equations and 9 unknowns. You can solve it. Can you see why we introduced Doolittle and Kraut method? Because if you don't use those methods, you cannot solve it. Because you will have 9 equations and 9 equations and 9 unknowns. To make this transition, you will need the help of two methods, Doolittle and Kraut. I hope you are understanding this. Okay. So this is the most important like way how why Doolittle and Kraut methods are actually needed. Okay. Maybe. Okay. Can I give you a question now for the next class after the lunch, which you can do just now? It's fine. It's very easy. I want you to gain the expertise, and we will see this in Python. Okay. I will just want you to do little. It's a very little thing. Do little. So the question is simple enough. So I want you. You have this equation. Okay, you have this equation. See, the main reason I am trying to cover this in this itself is so that a continuity is maintained in all the methods. Okay, else the continuity will be broken. Sorry, minus z. Okay. Now you can get the coefficient matrix, isn't it, from this? What is the coefficient matrix? 2 minus 3, 3, 6, minus 8, 7, minus 2, 6, minus 1. Now I'm asking you to convert this A into LU decomposition using Doolittle method. That means LII equals to 1, isn't it? So what you do, you write the matrix A in all ones. Can you tell me the matrix here? This is a 3 by 3 matrix, right? So 1, 0, 0. Some L2 1 you will have, but L2 2 is 1 again. L3 1, L3 2, but L3 1 is 1 again. Can you see that all diagonal elements Lii are 1? And this is the upper triangular times. You have to multiply with the upper triangular matrix. U11, U12, U13, 0, U22, 23, U33. Your job is to find the remaining Lij and Uij. Technically, from what we learned from the previous page, since we are using Doolittle method, you can easily solve this in the sense that there will be 9 equations and there will be 9 unknowns. So it is perfectly solvable. Your job would to find Lij and Uij. Okay. So after you do that, we will see how it is helping you to solve this Ax equal to B. Okay. With that, I think can you try it now a bit?